again. Now that we've got some of the theory out of the way, let's talk about how we actually find extreme values of a function on a closed interval. First thing we have to do is check the continuity over that interval. Remember that if it's not continuous, if the function is not continuous over the interval, there's no guarantee that there will be extreme values. Second, we're going to find any critical numbers for the function over that interval. We'll calculate the derivative, find any places where the derivative is 0 or undefined. Then, we'll evaluate the function at the endpoints and at any of the critical numbers that we found, and that will help us identify any absolute extrema. So here's our first example. Let's find the absolute extrema of the function x cubed minus 3x plus 1 on 0, 4. So the first thing to note is that this is a polynomial function, and so the domain is all reals, and it's continuous everywhere. All right, so it is continuous on 0, 4. All right, let's calculate the derivative. The derivative would be 3x squared minus 3. And let's set that, let's find any critical numbers. Setting it equal to 0, that's fine, we can do that. It's never, 3x squared minus 3 is defined everywhere, so there's no place for us undefined. So let's just set 3x squared minus 3 equal to 0. So then that implies then add 3 divided by 3, x squared is 1. And so x is positive or negative square root of 1. So x is positive or negative 1. Now, on our interval 0, 4, there's only one critical number. Only the positive 1 is critical on our given interval. All right, so now we will evaluate the function at the endpoints of the interval and at the critical numbers to identify the absolute extrema. We need to evaluate f of 0. We need to evaluate f of 1. We need to evaluate f of 4. All right, so f of 0 would be 0 cubed minus 3 times 0 plus 1. That would be 1. F of 1 would be 1 cubed minus 3 times 1 plus 1. That would be 1 minus 3 plus 1. That's negative 1. And then f of 4 would be 4 cubed minus 3 times 4 plus 1. That would be 64 minus 12, which is 52. 52 plus 1 is 53. So what do we see? There is an absolute minimum of negative 1 when x equals 1. There is an absolute maximum of 53 when x equals 4. So for this function, over the interval, there's the absolute extrema. That's it. The f of 0 equals 1. That doesn't give us any other information that we can use. So that's an example of how we can use critical numbers and the absolute value, the extreme value theorem to help us find absolute extrema for a function over an interval. Let's see some more examples. All right, so here's another function that's a polynomial over a given interval. This would be a good time to pause. Try this one out on your own. So again, we have a polynomial function. It was definitely continuous on the interval, the given interval 0 to 3. Let's calculate the derivative. The derivative would be 12x squared minus 30x plus 12. And let's set that equal to 0. 12x squared minus 30x plus 12 is 0. Now, I don't think this one's going to factor. So I'm going to go straight to the quadratic formula. I mean, We could factor out a 6, I suppose. It might make life a little bit easier. All right, so that's 6 by 2x squared minus 5x plus 2 is 0. Wait, does that that does factor. Okay, so that's 6 by 2x by x, and then put a minus 1 here and a minus 2 here, and it factors. All right, let's just check that. 2x squared, that works. Minus 4x minus x, that's the minus 5x plus 2, it works. So that means then 6 cannot equal 0, right? That's a constant factor. 2x minus 1 can equal 0. That would imply that x is 1/2. X minus 2 equals 0. That would imply that x equals 2. All right, so checking the endpoints and the critical numbers. We would need to now evaluate f of 0, f of 1/2, f of 2, and f of 3. All right, so I'm going to go ahead and use a calculator for this. So I'll bring up my calculator, and I'm going to go to the y equals screen here, and I'll input the function for x to the third minus 15x squared plus 12x plus 7. And then I'll use the table feature of the calculator. So let me check my table settings. I want my table, my independent line, I want that to be on ask. Okay, so it is. All right. Let me go to the table, and let me delete this other stuff that I've got here, and let's input those values. All right, so we have x equals 0. X equals, I'll just use 0.5 instead of 1/2, 2, and 3. So we have 7, 9.75, 3, and 16. 7, 9.75, 3, and 16. All right, so looking this over, I see an absolute maximum of 16. When x equals 3. And I see an absolute minimum of 3 when x equals 2. All right, let's see another example. So here we have a function x minus 2 cosine x on negative pi to pi. So this one may be a little tougher because it involves a trigonometric function. Again, this would be a good time to pause to try this one out on your own. The function x is polynomial, so it's continuous everywhere. Cosine x is continuous everywhere, so this function is continuous. All right, so we don't have any continuity concerns. Let's calculate the derivative. F prime of x would be equal to 1 minus 2 times the derivative of cosine x is negative sine x. So that's 1 plus 2 sine x. All right, so there's f prime of x. All right, it's never undefined. 1 plus 2 sine x is never undefined, so let's set it equal to 0 to find our critical numbers. So then that implies that sine x is negative 1/2. All right, now on negative pi to pi, where is the sign negative 1/2? Let's think of our unit circle, and we want the b coordinate to be negative 1/2. All right, so where is the b coordinate negative 1/2? So those are the points on the unit circle, but we need to think from negative pi to pi, so we have to use some negative rotations. So this would be a negative pi over 6 and a negative 5 pi over 6. So our critical numbers on the interval on negative pi to pi would be negative pi over 6 and negative 5 pi over 6. All right, so we'll need to evaluate f of negative pi f of negative pi over 6. Let's go in order. Numerical order, it would be negative 5 pi over 6 here. Negative pi over 6. And f of pi. Alright, this one we can actually, it's not too difficult to do just using our heads and by hand. F of negative pi would be negative pi minus 2 cosine of negative pi. The cosine of negative pi would be negative 1. So then this would be negative pi minus 2 times negative 1, negative pi plus 2. And so if pi is 3.14, negative 3.14 plus 2, that would be a negative 1.14. Negative 5 pi over 6, so that would be negative 5 pi over 6 minus 2 times the cosine of negative 5 pi over 6, the cosine of negative 5 pi over 6. That would be negative root 3 over 2. And so then that ends up as being negative 5 pi over 6 plus the square root of 3. I guess I can't do that one in my head. I'll approximate that in a moment. F of negative pi over 6, that would be negative pi over 6 minus 2. The cosine of negative pi over 6 is positive root 3 over 2. And so then this would be negative pi over 6 minus the square root of 3. And finally, f of pi would be pi minus 2. The cosine of pi is again negative 1, so that would be pi plus 2. And that one I can do in my head. That's 3.14 plus 2. That's about 5.14. All right, let's calculate the other two. Let's see. Negative 5 pi over 6. Let's add the square root of 3. So it's about negative 0.88. Alright, and what about negative pi over 6? Negative pi over 6 minus the square root of 3. That's negative 2.26, roughly. Alright, so then scanning over these, we see the absolute minimum. So here we have an absolute minimum of, let's use the exact value, negative pi over 6 minus the square root of 3 when x equals negative pi over 6. And we see the absolute maximum of pi plus 2. And that occurs when x equals pi. Alright. Now the function cube root of x times 1 minus 2x on the interval negative 1 to 8. This one is tricky. So be careful calculating the derivative and finding the critical numbers for this one. Alright, but now would be a good time to pause and try this one out on your own. Alright, so we have the function cube root of x times 1 minus 2x. That function is continuous over the entire over negative 1 to 8. There's no concerns about divisions by 0 on that interval, or square roots of negative numbers. Right, that's I should say even roots more generally. We have an odd root. So we're not worried about odd roots of negative numbers. So continuity is fine. Alright, let's calculate the derivative. Using the product rule, I'd have 1/3 x to the negative 2/3 times 1 minus 2x plus x to the 1/3 times negative 2. Let's use a little bit of factoring here. Let me factor out x to the negative 2/3. So then I'd have 1/3 times 1 minus 2x plus x to the 3/3, so that would be x to the first power, times negative 2. So then that's x to the negative 2/3 times 1/3 minus 2/3 x minus 2x. So minus 2/3 x minus 6/3 x, that's minus 8/3 x. So notice that we could rewrite this if we wanted to as, if we do a little bit of factoring, a little bit of manipulation, this is the same as 1 minus 8x over 3 times the cube root of x squared. Right, if we rewrote this, that's another way to rewrite this derivative. 1 minus 8x over 3 times the cube root of x squared. Now what this means is we have two critical numbers. So notice that f prime of x is undefined at x equals 0, because that would give us a 0 in the denominator. And f prime of x equals 0 when 1 minus 8x equals 0, which would then imply that x is 1/8. So we have two critical numbers. At x equals 0 and x equals 1/8. And they are both on the domain that we were given, from negative 1 to 8. All right, so let's evaluate. Let's do this in numerical order. F of negative 1, f of 0, f of 1/8, and f of 8. All right, f of negative 1 would be the cube root of negative 1. That's negative 1 times 1 plus 2. So that would be 3. So f of negative 1 is negative 3. F of 0 would be 0. Notice that the cube root of 0 is 0. Doesn't matter what we get in the second factor, but I'll write 0 times 1, which is 0. F of 1/8. The cube root of 1/8 is 1/2 by 1 minus 2/8. That's 1 minus 1/4. That's 3/4. And so that's 3/8. And then f of 8 would be the cube root of 8, which is 2 times 1 minus 16. That's a negative 15. And that would be negative 30. All right, so looking this over, the highest, the most positive value is 3/8. So then I have an absolute max of 3/8 when x is 1/8. And I have an absolute min of negative 30 when x equals 8. All right, let's look at one more example. X e to the negative x on the interval negative 1 to 2. Again, now would be a good time to pause and try this one out on your own. All right, so let's again, continuity is no issue here. It's continuous. X is a polynomial. The exponential function, e to the negative x, is continuous. Again, there's no divisions by 0, no even roots of negative numbers, so nothing to worry about for continuity. All right, we have a continuous function. Let's calculate the derivative. F prime of x would be, using the product rule, I'd have 1 times e to the negative x plus x times e to the negative x times, from the chain rule, negative 1. Right, the derivative of e to the negative x is e to the negative x times the derivative of negative x. We can do a little factoring here. That's e to the negative x times 1 minus x. Now, this is never undefined, so let's set it equal to 0. So e to the negative x by 1 minus x equals 0. E to the negative x can't equal 0. 1 minus x equals 0 implies that x equals 1. So that's our only critical number. And so let's evaluate. The function at -1, the function at 1, the function at 2. Since this involves exponentials, I'll go ahead and use a calculator at some point, but this is really, the actual evaluation is not difficult. The approximation is difficult because of the exponentials. F of -1 would simply be negative e to the first power. Right? -1 times e to the opposite of -1. F of 1 would be e to the negative first power. F of 2 would be 2e to the negative second. Now, I'm not good at approximating that exponential in my head. I know e to the first power is about 2.718, so I know this one is approximately -2.718. And I know that's going to be the minimum because it's the only negative value, right? E to a negative power is positive. So now it's just a matter of calculating these. So let's calculate e to the negative first. So that's about 0.37 to 2 decimal places. And then 2 e to the negative second is about 0.27. So this one's approximately 0.36. This one's approximately 0.27. So this is my absolute minimum. I have an absolute minimum of negative e when x is -1, and I have an absolute maximum of e to the negative first when x equals 1. So that shows how we can find absolute extrema over a closed interval. Now, in a later topic, we're going to talk about, well, what if we wanted to find the extrema for a function over an open interval, or over the entire domain of the function? And for that, we need a few more tools. We're going to learn how to work with the first derivative and analyze a function completely with the first derivative, and that's going to help us with that. But that's a couple topics down the road. Alright, so that concludes this video for extreme values. I'll see you next time.